This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
My name is Vince Resch. I'm professor of the graduate school in the Department of Environmental Science, Policy, and Management, and I'm chair of the Hitchcock Lecture Committee. We're pleased, along with the Graduate Council, to present Dr. Ralph Cicerone, this year's speaker, as the Charles M. and Martha Hitchcock Lecture Speaker. As a condition of the original bequest, we're obliged and happy to tell you about how this endowment came to Berkeley, because it's a story that exemplifies the many ways this campus is linked both to the history of California and to the Bay Area. Dr. Charles Hitchcock was a physician for the U.S. Army who came to San Francisco during the gold rush and set up a private practice that was actually quite thriving. In 1885, he established a professorship here at Berkeley as an expression of his long-held interest in education. His daughter, with a very familiar name, Lily Hitchcock Coit, still treasured in San Francisco for her colorful personality as well as her generosity, greatly expanded her father's original gift to establish a professorship at UC Berkeley, making it possible for us to present a series of annual lectures. The Hitchcock Fund has become one of the most cherished endowments of the university, recognizing the highest distinction of scholarly thought and achievement. And we really want to thank both Lily and Charles Hitchcock for making this possible for so many decades. And now let me give you a few words about our speaker, Dr. Cicerone. Dr. Ralph J. Cicerone is president of the National Academy of Sciences and chair of the National Research Council. His research is focused on atmospheric chemistry, the radiative forcing of climate change due to trace gases, and the sources of atmospheric methane, nitrous oxide, and methyl halide gases. Cicerone has been credited with shaping science and environmental policy both nationally and internationally. He received the 1990 Bauer Award and Prize for Achievement in Science from the Franklin Institute for his fundamental contributions to the understanding of greenhouse gases and ozone depletion, and for his public policy leadership in protecting the global environment. In 2001, he led a National Academy of Science study on the current state of climate change requested by President Bush. Dr. Cicerone notes that in today's lecture, he'll use up-to-date data to illustrate the driving forces of greenhouse gases and contemporary climate change. Tomorrow, he'll give a second lecture in the same place where he'll compare successful initiatives to protect the ozone layer with the, to date, unsuccessful initiative to stabilize global climate. A prolific author, Dr. Cicerone has co-authored scores of publications, including the article, Trends of Extreme Precipitation in Eastern China and Their Possible Causes. He has also contributed to a wide variety of other articles, including physiological, biochemical controls over methyl halide emissions from rice plants, and biogeochemical aspects of atmospheric methane, a wide variety of topics. Our speaker holds a BS in electrical engineering from Massachusetts Institute of Technology and a PhD from the University of Illinois. In 1970, he began his research career at the University of Michigan, where the Ralph J. Cicerone Distinguished University Professorship of Atmospheric Sciences was established in 2007. He performed further research at Scripps Institute of Oceanography at the University of California, San Diego, and the National Center for Atmospheric Research in Boulder, Colorado. In 1989, he joined the University of California Irvine faculty, where he served as the founding chair of the Department of Earth System Science and the Daniel G. Aldrich Professor of Earth System Science. He was also dean of the School of Physical Science and chancellor of the university. In 2005, he was elected the president of the Academy of Sciences. Please join me in welcoming Dr. Cicerone to Berkeley.
Well, thank you for the kind introduction and also the opportunity to be here in the first place. I've already had a very stimulating day meeting with some Berkeley students and faculty members and research, and it's really a fun place, as it always has been. I enjoyed hearing that brief history of the Hitchcock influence here, so that was really endearing in a way and shows the value of support, I hope. What I want to do today, as Dr. Resch just mentioned, tomorrow I'm going to give a second talk focused much more on how the world is responding to these physically identified and measured challenges to the physical environment that supports us. Today I'm going to focus more on the science behind climate change, largely showing data of some key variables, what's actually being measured, and what do we know and what we don't know. And then I'll end with a few comments on how to advance that science. So let me show you an outline of what I want to do here. This is an outline of what I'd like to cover. First of all, a concept that I think is a really good organizing concept for trying to understand the climate of this entire planet. It's largely a global scale argument, but it's physically sound. Then I'll get right into the data, things that are being measured, the observed changes in recent decades in important variables, the temperature of air, the temperature of water, the budget of the ice masses hung up on the continents of Greenland and Antarctica, a little bit about sea ice, sea level rise, Arctic sea ice, and then a reminder of what one of the major driving forces is, human use of energy from fossil fuels, and then some comments about moving the science forward. Because an ultimate goal of this science is not only to understand and to measure what's happening and detect the changes, but to try to anticipate what's coming so that human adaptation as well as mitigation efforts can come into play more effectively. And then, of course, try to predict those changes at the same time. So the first concept is simply that the energy balance of the planet controls the Earth's climate. This is not an astounding observation, but it's an organizing framework that really allows us to focus on important variables and to measure just how far away from a static situation we are, for example. So this is more or less a cartoon looking at the Earth with the sun, not to scale, but to a very good first approximation, very good approximation. The energy budget of the Earth is balanced by incoming sunlight, largely visible sunlight, some infrared that's important, and outgoing radiation from the planet, which is planetary infrared radiation. So the balance is, these quantities have been measured fairly well to within 1% of almost everything I show here. Coming in from the sun, on average, is 341 watts per meter squared. So it's energy per unit time per meter squared. And about a little bit less than 1/3, 30% of that energy, 102 watts per square meter, is reflected back out to space before it's ever received by the Earth's surface by white things, by light-colored objects, whether it's clothing or whether it's ice and reflective water. So the net, 341 minus 102 watts per square meter, is the net incoming radiation from the sun, and the outgoing is, as I said, infrared light at 239 watts per square meter. And these two quantities are remarkably well balanced from all the measurements that have been made largely by Earth orbiting satellites. The shuffling around of that energy, once it's absorbed by the dark surfaces on the Earth and re-emitted in the form of either measurable or infrared radiation, bounces around here, and it maintains a temperature where the Earth's surface is higher than that of the atmosphere and so forth. And the numbers are fairly well known on average. So to a first approximation, that's the budget, and anything that can be done to perturb that budget is capable of changing the climate either towards, let's say, a planetary average lower temperature or a higher temperature. This satellite, or this picture, this graph, was created in 1972 from one of the first Earth-orbiting satellites that was looking down at the Earth in the infrared. And what it shows is, as a function of wavelength, 10 micrometers and so forth, how much radiation was seen by the satellite looking down on the Earth. And if the Earth were radiating just as a black body radiator, you would have these curved, dashed curve if the temperature were 300 Kelvin or 27 degrees centigrade. Or if the Earth were very, very cold, you would get this curve. But what was actually measured has structure in it, and they indicate the presence of greenhouse gases in the atmosphere. That is, chemicals that float around in the air in gaseous form that have the ability to intercept outgoing infrared radiation, this energy that I referred to. So this absorption is mostly by atmospheric ozone. This absorption is due to mostly carbon dioxide. In between, there's a lot of water vapor absorption. So the point is, there's no mystery here. One can go into the laboratory and measure the wavelength dependence of the way these gases interact with infrared light, for example, and do quantitative calculations, and you can calculate that this is what you should see looking down on the Earth, things like that. So just to do a rough calculation, this idea was pointed out probably 40 years ago, that we can calculate the temperature of different planets, Earth, Venus, and Mars, the ones that we know the best. So for example, if you do this calculation for Mars, this equation applies in steady state, that is, nothing's changing with time. We now know that things are changing with time, but just to a first approximation, if you know the total amount of sunlight energy coming in, and the fraction 30% is reflected, that means that 70%, 1 minus 0.3, is absorbed by the Earth and the atmosphere. That should be equal to the outgoing radiation, which in equilibrium would be the sigma t to the fourth law. So S is measured, alpha is measured, sigma is a constant. You can calculate temperature just by taking the fourth root of the equation, and you get for Mars that the temperature is something like minus 28 degrees centigrade, and it's the right answer, within a few degrees if you average over day and night. If you do the same calculation for Earth, you don't calculate the right number. You calculate that Earth is freezing everywhere all the time, and what's missing here is the greenhouse effect of the gases that I just mentioned. Mars has a very thin, low-pressure atmosphere. There's not much in the atmosphere that interferes with the light coming in or the infrared going out. So you can calculate Mars in this simple way, the temperature very accurately. With Earth, as I said, you miss by about 50 degrees centigrade. And for Venus, you really miss, because the atmosphere of Venus is very thick, pressure 100 times that of Earth, loaded with carbon dioxide and other greenhouse gases. So this calculation illustrates that right away you're pretty close to the right answer just by including greenhouse effect and clouds. Well, why is all this important? Because we know now that the chemical composition of Earth's atmosphere is changing. This is the iconic series of data taken mostly by people at Scripps Institution of Oceanography. David Keeling, who's now deceased, and his son, who's a professor there, Ralph Keeling, has continued the measurements. Every black dot, if you can see it, represents the average of measurements of carbon dioxide in air up the slopes of Mauna Loa on the Big Island of Hawaii, sampled every 1 hour. So every black data point, as I said, is the monthly average of measurements made every hour. And what you see is the underlying trend has gone up, starting from 312 parts per million in 1957 up to about 400 last year, although this graph was updated in January. The red curve is the same kind of measurements from the South Pole. So there's a few months lag time when they ship these little containers of gas back and forth. On top of that underlying rise is this annual cycle, wiggling of the carbon dioxide amounts, which is really quite beautiful, and it's telling us something about the Earth as a living planet. In the summer and spring, for example, the Northern Hemisphere months, when photosynthesis is happening and green plants and algae and water bodies are sucking in carbon dioxide for photosynthesis, the carbon dioxide amount is drawn down, and then in the fall and winter, subsequent respiration and decay of that, some of that new organic matter takes place. So every year there's an annual cycle, drawing down CO2, reintroducing CO2 into the atmosphere, on and on and on. There's an offset from the South Pole for other explainable technical reasons. And there's not much land surrounding the South Pole, so the air that one samples doesn't show these kind of seasonal wiggles. There isn't much photosynthesis there at all, even in the surrounding waters. Okay, let's now get down to variables that are being observed that tell us something about climate change. First of all, air temperatures. In another slide, I'll show you the names of some Berkeley people who've done some similar analysis. But first of all, this temperature scale, 0 does not mean 0 degrees. It means a reference point. And that reference point is the average of all the temperatures measured between 1950 and 1980. So it's a 30-year data set which is used to establish an average. And in this case, the average was 1950 to 1980. So 0 corresponds to the average of this 30-year period. Anything that's negative from that 0 represents times when the Earth's temperature, on average, averaged over all latitudes and longitudes, day and night, was lower than the 0. And of course, in later years, beginning about 1975, the measurements of these air temperatures have gone up, more or less monotonically. There are a few 100 million data points in this data set, and the statistics are pretty good. You'll see that the record year of 2015 really was high compared to all previous years. A previous El Nino year, when the eastern tropical Pacific waters are warm, was 1998, which was also a high year. But the underlying trend, again, is increasing air temperatures all over the world. There are several other laboratories. These data happen to come from a NASA laboratory in New York City, the Goddard Institute for Space Studies, which is the reference here, which you can pull these off of their website anytime. Very well documented. All the changes in the record are explained. Any so-called corrections to the data, adjustments to the data stream are explained in great detail, very well documented. And there are 3 or 4 labs around the world who do similar work with slightly different approaches and different data sets, and I'll mention that in a minute. Just to show you the kind of detail that's available to start to break this down, because a global average temperature, in the words of someone one time long ago, he said, "That doesn't make my knuckles white." He didn't know how to respond to that. So a global average temperature is relevant because of the framework that I mentioned, the concept of a planetary energy balance, but it doesn't really tell us a lot about what's coming. The Berkeley Earth Temperature Project, which I mentioned, examined the same kind of data over a period of years, and overlaid over the previous data, the NASA data, you'll see that they obtained very, very similar results, but with very different approaches. They used different data sets. They tried to introduce different ways of correction for things like the urban heat island effect. In many of the places, for example, in developed countries like the United States, where temperature recording instruments have been put out, cities have grown around them and surrounded the place with blacktop. And you can see the urban heat island effect all over the world. And this Berkeley project, led by Rich Muller, but also the other people listed here, not all of whom are from Berkeley, they tried to see what the sensitivity of the record is if they cut the data up into different pieces, removed individual stations from the record of which they were suspicious, gave more weighting to the ones that looked like they were well maintained and so forth. And on this scale, the results are the same, at least on the global average temperature. This is a very valuable project that was performed here. that I think answered a lot of serious questions very well. Now, let's break the data down a little bit into all land and ocean areas north of the equator, northern hemisphere annual mean versus southern hemisphere. And you'll see that the northern hemisphere in the red has warmed up more than the southern hemisphere in blue. And now that's logical because the southern hemisphere has more ocean area in it than the northern hemisphere does, so the heat capacity near the surface is greater. And if, for example, this is being forced, these changes are being forced by the physical imposition of new energy, like this greenhouse effect that's growing, you would expect to see a lag that the southern hemisphere would warm more slowly. So not only are these data real, but they seem to be consistent with the underlying premise here. If you break those data down further, and these are now surface temperatures measured at different places around the world. So here's an outline of South America, North America, Africa, and so forth. You can see the outlines with false color codings showing 3 of the warmest winters in this 135-year record. 2015 was the warmest at all, and you'll see the preponderance of really hot areas where the temperature is 4 or 5 degrees centigrade warmer than the average period over an entire year, and a little bit of cooling in part of the Antarctic sector. Most parts of the world, though, are showing excess warmth, higher temperatures. When you plot 10 or 20 years together, you find that there's virtually no place on the Earth that has remained at its average or is below average. Everything is up. So 2015 looked like this, 2010 was like this, even more pronounced warming over this part of the Arctic and so forth. There's a month-by-month record of this anomaly again, that is the amount over the 30-year average, and it shows the hottest years. So for example, 2014 in green shows the global average temperature month by month, September, October, November, December, and so forth, and some ups and downs during the year. 2015, the record for any month before 2015 is this black line, and then in 2015, records were set over the 135-year period of observations for the months of October, November, December, and they continued into January of this year. So this is now a plot of January mean surface temperature over these parts of the world, where now this pink is the hottest of all. Parts of the Arctic are 10 and 12 degrees centigrade above the 30-year average. This turns out to be a puzzle. It's hard to say why the Arctic is warming up maybe twice as fast as anybody expected it to. So the point is, these data are available pretty much on a monthly basis. You can track these things, and in even more detail, because most of the significance of climate change, impact on humans and ecosystems and so forth, will be regional in individual locations. But this globally average picture and the geographical projection, different parts of the world, is still interesting to understand. So here's January of 2016 compared to all previous hot Januaries. It's way up there. Now, temperatures of ocean. It's harder to get really tight data on ocean water temperatures because they're not as well sampled. The sampling is much coarser geographically and in time. But over the last few years, due to some very careful work, this graph happens to be from somebody named Levitas, who's recently retired from our National Oceanic and Atmospheric Administration. They have plotted the change in the heat content of water bodies around the world. This is a little bit complicated, but 0 would be if there were no change in the heat content. So here is a graph of the world ocean heat content broken down versus altitude below the surface of the ocean. So the thermocline, the body of ocean water, which is pretty well mixed above 700 meters, below that point 700 meters below the surface, has increased by a few hundredths of 10 to the 22 joules per year. But you can see that it's as if a heat pulse is sinking now into the ocean, and it is seen first at the lower depths, a few hundred, the more shallow depths, and it's propagating now down into the deeper depths, the greater depths with time. And when you do the numbers and add it up globally, this amount of extra heat that's being observed by real measurements in the ocean is compatible with the budget figures that I'm showing you on Earth's energy budget. This kind of data is now becoming much more available due to the invention of some automated floating devices which go around the world's oceans and measure several things about the ocean waters, and that they can bob up and down under control and sample great depths, and they do it repeatedly. It's a fantastic set of instruments. So these data sets are growing. These are some of the first patterns that are emerging. This graph's maybe a little easier to see. It shows what's observed in the 0 to 2 kilometers depth, so the increasing heat content, which is essentially temperature, with time at all depths. Again, the data are still coarse. There are some undersampled regions. In fact, this bar gives you a measure of whether or not the layers are being based and what fraction of the waters around the world are being measured at various depths. So these data are increasing. They also show a warming, especially over the last 30 or 40 years or 50 years, all around the world. And it's clear that the rate at which the heat is being sucked into the world's oceans is not very predictable at this time. It happens somewhat sporadically at different latitudes, but on average, the numbers are looking pretty consistent with all this other picture. You've probably seen photographs or some kinds of measures of the amount of ice floating on the Arctic Ocean. Now, that floating ice is not serious in terms of sea level because it's already floating. It changes from solid to liquid. It doesn't change the sea level. But from a point of view of navigation, mineral exploration, commerce, military security, the amount of sea ice is important, and it's an interesting variable. So these data are reported almost daily from a remote sensing device that has been operating since about 1980. So the gray plot here, the shadowed plot, represents the amount of sea ice measured in extent, millions of square kilometers in the Arctic Sea, plus or minus 2 standard deviations of the average. So if you take this 35-year average of these measurements, they all fall within this gray band. 2015, 2016 is scraping the very bottom. It's down 2 standard deviations or so from the average, and this is pretty much typical of the last few years. 2012 was also very low, a little bit of recovery in between, but the new norm is the Arctic sea ice disappearing. One of the plots that's a little bit more telling is take just the month of January every year since 1979 and ask how has the average amount of ice in January in the Arctic Ocean changed, and it's going down monotonically. In fact, because of those very high temperatures seen in the Arctic that I pointed out earlier in the air temperatures, this January of 2016 is pretty low. There are similar plots for June, and they showed similar patterns that the amount of ice floating in the Arctic is decreasing pretty well monotonically over the entire period of measurements. There are other measurements, which I'm not going to show here, of the thickness of the sea ice, the ice that a submarine would have to penetrate to get out of the ocean. And due to some military data from the US and the former Soviet Union that's been declassified, we can see about a 60% decrease in the Arctic sea ice thickness over the last 40 or 50 years. So these data are also consistent. The Antarctic's a little more complicated and the data are not so clear, and I won't show them here. One of the most stunning measurements, which I can explain a little later, but it takes more time, is how the mass of ice on Greenland and Antarctica is being measured. It's done by remote sensing with an instrument that actually measures small perturbations in the Earth's otherwise spherical gravitational force. It's a very neat technical setup. And what they have shown, these data only go up to about 2014, is that there are seasonal changes in the amount of ice on Greenland, but generally speaking, the annual average has decreased, and it's decreased by, on average, 260 gigatons of ice per year that is falling off the Greenland continent or melting directly into seawater. And if you'll notice, that's an inverted parabola. It's not a straight line. It shows an acceleration of the rate of loss of about 30, I think it is, 28 gigatons per year as an acceleration. And these data are not only really high tech and well done, but they're confirmed by other measurements of the height of the ice extending over the Greenland continent. Similarly for Antarctica, this was just a huge drop in 1 year, but there was some recovery after that. These data are from Isabella Villacogna and her colleagues. She's a physicist in my home department, Earth System Science at Irvine. Her senior colleague, John Warr, unfortunately died about 8 months ago now, but this data set continues. Okay, when they look at Antarctica, they find a similar picture with more variability. Again, over the 11-year period, there's been a loss of the ice mass on Antarctica. It's been not as strong, a lot more annual variability. In fact, they can now focus the instrument better on sectors of Antarctica, where they find that there is one sector of Antarctica which is net gaining ice, and the major part of Antarctica is losing ice, but it's more messy data. But they also find an accelerated loss of mass and ice on Antarctica. Now, the reason this is important is when you lose ice from a continent and put it in the ocean, sea level rises. So if you add the contribution to sea level rise of Greenland and Antarctica, you'll get numbers that I'm getting to now, which is pretty well explaining the observed sea level rise. This graph is a record of rather old measurements of sea level over the beginning of the 20th century all the way through the 21st century. And most of these data in the black curve were obtained by basically tide gauges, stakes and poles pounded into the coastal environment, fairly primitive instruments, but very, very careful record keeping has allowed a reconstruction of sea level over the 20th century, about a 110-year period up to 1992. If you average all of these tide gauge records from all over the world, you see this indicator of global sea level rise. And there's certainly some spots which are geologically active, tectonically active, where the rise has been less or more over time, and the statistics of these measurements are a little bit scattered. But beginning in the year 1992, Earth orbiting satellites with radar ranging devices and some interferometry added to it have shown the red part of the data, which is a somewhat faster rise in sea level, which is a better global average, much more precise, better sampling. And it shows, since 1992, here's what that record looks like. The observed sea level rise, the best fit to the data, is about double what I showed from the old tide gauge record. It's 3.3 millimeters per year over this modern record of altimetry from remote sensing satellites. So the question arises, has sea level rise accelerated? Because the earlier result was about 1.6 centimeters over 100 years, or about 1.6 millimeters per year compared to this 3.3, double. Well, recently, a couple of people have analyzed these old records, and they think that the statistics are a better fit to a slower rate of sea level rise here, increasing more to match the red modern observations. So it's a minor refinement, but it adds evidence to the idea that sea level rise is accelerating. And the budget now of where the water is coming from gives a pretty good first approximation to this observed rate of sea level rise. These data are also updated every 3 or 4 months by a group at University of Colorado who are in charge of this remote sounding instrument. And you can see that the last few months have been higher, but the best fit to the data will probably be still about 3.4, 3.5 millimeters per year. Now, where does that come from? The very fact that sea surface temperatures are being warmed, the temperature's rising, causes a thermal expansion of layers of ocean, and that accounts for maybe a third or a half of this observed sea level rise over the last 30 to 40 years. The rest of the rise in sea level is coming from new water being dumped in from melting ice in Greenland, Antarctica, and some inland glaciers. There's also a drawdown which can actually be measured in some of these wiggles when there are huge dumps of rain, as there was in Australia in 2010 and 11. There was enough water dumped in Australia that did not make its way off of the continent into the oceans to cause a decrease in sea level. So these instruments are quite capable now, but that's the rough picture. So going back to the carbon dioxide record, I want to make the point now of something being unusual here. Namely, we now have observations from ice cores in Greenland and Antarctica that have been dated. That is, you can drill down and take a vertical core out of the ice and put dates on it. This was from 100 years ago, a little bit deeper was from 200 years ago, 1,000 years ago, and so forth. One of the most important sets of data came from an international collaboration led by French, who drilled a very deep ice core at the Vostok area of Antarctica. And it's so deep that it went back 450,000 years from the present, before present, 200,000 years before present, 300,000 years before present, and so forth. And what they found was, by slicing up the ice at different depths and crushing the ice, they could extract the gas that was trapped in that old ice. For example, carbon dioxide. So this is a physical measurement of how much carbon dioxide was in the air 100,000 years ago, 150,000 years ago, and so forth. It's a direct measurement. So this is a major accomplishment. And what it shows is that there have been different ice ages. There was an ice age about 20,000 years ago that hit, and then 140,000 years ago, another ice age about 250,000 years ago, and so forth. When it was cold, the carbon dioxide amounts in the air were not 400 parts per million like it is now, but 180 parts per million. And when it was warm in between ice ages, it was about 270 or 280 parts per million. So going back one ice age, I just did, going back two ice ages, also low, in between ice ages, high, namely 280 parts per million, in between ice ages, and so forth. So whatever is causing this, it shows that the chemical composition of the air today is unprecedented. The last four global ice ages and the last four in-between warmer periods had carbon dioxide bracketed at concentrations down here, and where we are now is completely out of that range. So there are many ways to prove that the excess carbon dioxide today is due to fossil fuel burning. And I won't go into them now, I could illustrate it later. But whatever the cause is, we can prove definitely that the carbon dioxide content of Earth's atmosphere today is above where it's ever been in this kind of recorded history. We think that 50 million years ago, Carboniferous period, 100 million years ago, there was more carbon dioxide, but it's, of course, hard to be sure. The same is true of another greenhouse gas, methane, where the blue curve here is a proxy measurement of what the temperature was, inferred from ice amounts and the isotopic content of the ice cores. But when it was cold, methane amounts were about 1/3 of a part per million, and when it was warm in between ice ages, methane amounts were about 2/3 of a part per million. Methane amounts in today's atmosphere are about 1.9 parts per million, so 2 to 5 times what has ever been seen before. So this set of ice cores from the French, the Danes, the Russians, with some contribution from Americans, is really very important. It tells something about where we are today being unprecedented in terms of climate history, at least back 800,000 years. The data have now been extended back 800,000 years. This is just an example to show what we see in nitrous oxide measurements, another greenhouse gas, whose origin is not as clear, but it seems to be involved with a number of human activities, including artificial nitrogen produced for fixed nitrogen for fertilizers. So, what does that have to do with the energy budget of the planet? Now we can take, and have taken over the last 35 years or so, laboratory measurements that tell how these gases interact with outgoing planetary radiation that would otherwise escape to space. We can do quantitative calculations then, knowing the amounts of these chemicals added to the air since the Industrial Revolution, determined by measurements of recent ice cores in the same way, compared to what's measured now. And when you do that, you can then calculate what is the change to the Earth's energy budget at the surface. So just the carbon dioxide added amount gives you almost 2 watts per square meter extra energy per unit time trapped in the Earth's lower surface areas. Methane gives this contribution, nitrous oxide, some fluorocarbon replacement chemicals, hydrofluorocarbons, some perfluorinated chemicals, CFCs, and then ozone in the lower atmosphere. And the answer comes up to be about, if you add all these together, almost 3 watts per square meter. We call it radiative forcing, but it means forcing that will directly affect Earth's climate. There are more complications in this radiative forcing, which I'll mention also later, but that's the simple side of it. So there's something else that's different about this last 30 or 40 years, in addition to what I've just showed you of the actual measurements of air and water temperatures, ice amounts, sea level rise. And that is, it's the first time in human history that we've been able to measure the output of the sun with enough stability and precision to say, well, maybe the sun's energy reaching the Earth has just increased at the same time. Maybe these warming phenomena are simply due to extra energy coming from the sun. Well, the answer is no. These results were published about 2005 by Judith Lean, who's a scientist with the US Naval Research Lab, and a colleague, Klaus Freilich, in Switzerland, that shows that over this period of satellite observations of the sun with some precision, there was no change in the amount of energy coming out of the sun, except for a little bit of an 11-year cycle that correlates with sunspots, which we've known about for a long time. And in fact, this whole change is about 0.1% from top to bottom. Well, the number I just showed you, the radiative forcing due to greenhouse gases, are about 1.5%. And the change due to solar irradiance is about 1/10 or 1/20th of that amount. The difference here is you have to get there's a geometrical factor. The amount of energy actually being intercepted by the Earth is this number divided by 4. Some of you who are arithmetic freaks may have already realized that if you divide this number by 4, you get 341 watts per square meter, which was on my first cartoon slide. That's the geometrical factor. So now that record has been difficult for Freilich and Lean to put together because it required stringing together satellite observations with high precision that weren't meant to be used that way, but they've continued the work, and this is Klaus Freilich's recent update showing now 3 or 3.5 solar cycles, 4 solar cycles, again, with a cycle. So the radiative forcing due to the greenhouse gases is not a cycle. It's a sustained elevation in the energy budget of the Earth, whereas these cycles are just that. They are imposed by solar activity changes, and they're smaller. So the greenhouse gas forcing is about, at the surface, about 3 watts per square meter, and this one is 0.25 watts per square meter, wiggling around. So those of us who thought and hoped that maybe the sun's output was causing these changes when we were thinking of this back in the early 80s, we no longer have a leg to stand on. The evidence is really clear that these physical changes that are being observed are very strongly linked with human activity. The numbers add up, the processes add up, the mechanics, the underlying premise. Well, I'm going to close in a few minutes, but why do we care, and is this likely to continue? Well, if you just look at one of the greenhouse gases, carbon dioxide, where it's coming from, of course, you all know about the burning of fossil fuels. That is, burning of substances like natural gas, coal, wood that contains carbon. The very act of burning the stuff in air creates carbon dioxide. And the thermodynamics is that the heat released in that oxidation of carbon to release carbon dioxide is what gives us the heat and the energy. So it's very valuable right now. However, if you look at the carbon part of it and how much carbon dioxide is being released, there's this figure called global. This is from a woman named Corinne Lecaire with a paper that was just released a month or two ago where they've gone back over all the carbon budgets of all the, and they didn't do this alone. There were many, many, many assessments before they did this, but this is in a peer-reviewed journal showing that if you just look at the fossil fuels being consumed around the Earth and ask how much carbon is being released in the form of carbon dioxide, the number today, the year 2012 or 14, is about 10 billion tons of carbon per year. So obviously, carbon dioxide is 44 divided by 12 times as much, but just look at the carbon release as carbon dioxide. It's 10 or a little bit more than 10 gigatons, 10 billion tons. A breakdown is that on the lower graph here, about 40% of that carbon is being released from coal combustion, about 30% from oil combustion, and you see gas and cement manufacture, which also releases carbon as carbon dioxide. Well, this source of energy for human activities is about 80% of all the energy that humans use on the planet. That is for manufacturing, for transportation, for production of electricity, you name it. The remaining 20% is from hydropower, nuclear power, solar and wind power, which of course are gaining, but they all add up to only 20%. So for the foreseeable future, there will be continued large emissions of carbon dioxide into the atmosphere. And I can give you more evidence on why we know that this is from humans and got the numbers right. It's pretty compelling evidence. But even as the world tries to conserve energy, to be more efficient, and to use renewable energy, it's very hard to escape that there will be continued large emissions of carbon dioxide. For one thing, just for transportation. When you burn gasoline or diesel to drive a car or a truck, it's actually a pretty well-suited fuel because you don't have to carry the oxidizer around with you. You get the oxidizer, oxygen, out of air for free, and you don't have to transport it while you're going. You're carrying only the minimum load of fuel that you need. You don't have to carry the oxygen with you. It's not like a spaceship where you have to carry the oxidizer with you. So hydrocarbon fuels have a big advantage, and they're not going to be displaced easily. It costs virtually nothing to extract them from the ground, and so forth. On the other hand, the progress in providing energy for industry and residents and everything else, electricity from renewable power and from progressively better nuclear power, it's non-trivial. but it can't handle much of the load. This is a further breakdown of LaCara's data, nation by nation for a few nations, showing that the fabulous economic growth in China. China is now the world's #1 CO2 emitter. It's not only due to their economic growth, but the displacement of heavy industry from the United States and other countries to China. So there's been a structural change in their economy. They're doing more of the heavy manufacturing, which has also led them to release more CO2. India is growing fast. But per capita, you can see that the per capita emissions, that is tons of carbon per person per year, the US is still the most at about almost, what does that say? About 5 tons per person per year. The global total, or the global average is less because India and China and the European Union and so forth emit less per person. So no matter how you slice it, these global data tell you that there's going to be very hard to change this trend. So that means that whatever is happening with climate, we really have to get better at making predictions and assessing it. So just a few observations on how we can move the science forward. And some of you here are doing some very important work in this regard. But to make the science more understandable, more definite, to refine the trends, and to make better estimates of what's going to happen in the future, let alone predictions, we clearly have to extend and improve the observational record. For example, the ocean measurements and the ice measurements. We have to create longer records and deduce the trends and patterns more carefully. For example, sea level rise. Extreme weather events is really where a lot of the action is. It's not just average temperatures that we're concerned about. It's precipitation events. How many big rain dumps and big snow dumps do people get? How long are the heat waves? How long are the droughts? What is the odds of floods happening? Some of the world leaders in these questions are insurance companies and the reinsurance industry, largely in Europe. They probably have the best statistics on what's happening, and they break it down into physical events as well as financial claims that they have to pay. But the physical predictions are pretty difficult, and yet they're incredibly important. It's not just the averages, it's what are the extremes that are happening, and I'll give you an example of this. Then we also want to know whether those the changes that we are observing in the frequency of these extreme events, what does it mean in terms of attributing? Has a particular storm happened because of climate change, or has it just happened randomly? And what are the return times? You hear these stories about 1 in 500-year floods, 1 in 100-year floods. Do we really know that that's a typical return time? And how can we do a better job at estimating those return times for better public planning, for insurance applications, and so forth? Let me go to the next slide and show you something. If you take the same temperature data that I showed you earlier, this happens to be, again, the NASA GISS data, and you go decade by decade. In the reference period, the 30-year reference period, this is now Northern Hemisphere land in June, July, and August. You could divide up what looks like a normal distribution of temperatures into 3 parts. The lowest 1/3 of temperatures on average in that Northern Hemisphere summer period, the middle part, which also contains 1/3 of the observations, and the upper part, the highest temperatures. Now march that forward to the actual data in the next decade, and you'll see things shifting to the right, although this is 1983 to 1993. In that lower third, you now only have 23% of the data. In the middle third, you have whatever that number is, and 47, 48% in the upper right. If you go now into the latest decade, 2005 to 2015, look what's happened to that distribution. It has shifted to the right. These are actual data. And you see that what used to be the population in the lower 1/3 of the data is now only about, I think it's 12%, I can't quite read it. In what used to be, the normal distribution is now characterized by these higher temperatures that used to be a couple of standard deviations to the right, now showing up 67% of the time. And places way to the right, like 4 standard deviations above normal, are now happening 15% of the time. So a slight shift to the right gives you a much larger frequency of high temperature events and a much lower frequency of low temperature events. But this is now averaged over a big piece of land, the northern hemisphere over the summer. If you do the same thing northern hemisphere in the winter, you get similar results. So this is one kind of low-level reason to expect the frequency of extreme events to change. Hotter temperatures in the summer over land, and warmer temperatures in the winter over land with less real freezing events. I mentioned radiative forcing before. There are complications to those numbers I showed you. Floating aerosol materials, some of them have ability to reflect sunlight back out to space, visible sunlight, especially sulfur-containing particles. So trying to do these calculations in a reliable way is difficult, because we don't actually know at any one time how much of this floating aerosol material there is in the air from sulfur-containing fossil fuels that, when burnt, create sulfur pollution. This input is probably being reduced worldwide now, but when you try to add that to the radiative forcing numbers I showed you, we get big uncertainties of about a watt per square meter that could be negative. We also don't know the geographical distribution and temporal changes in that aerosol material, so it's a measurement challenge. Ice losses and sea level rise are particularly important because of all the climate changes that you want to talk about. The most dangerous kinds, the worst risks, are changes that are irreversible, such as sea level rise, or irreversible, for example, biodiversity loss. You can't replace species. At least those are 2 examples. So with sea level rise, the good news is so much has been learned in the last 6 or 7 years about where the ice is plunging off of Greenland and Antarctica. There are specific sites where the ice mass loss is happening due to ice sliding down the sloping continent that is being held up by an ice shelf. And as the shelf gets undercut by warm water and gets dissolved, then you get an acceleration of the ice mass sliding down the slope. These sites have now been mapped out pretty well, and there are a lot of unknowns, but at least people know where to do the measuring now, where to measure the water temperatures, and how much the melting of the shelf is being undercut and the ice can slide off. So that's progress, and it will represent a better predictive capability. There's still some argument whether ice shelf melting that I just illustrated with my hands is the dominant mechanism, or is it simply ice fracturing? It's probably more ice shelf melting undercutting the ice shelf. But then as this accelerates and more of this cold water comes running off of Greenland and Antarctica, it's going to affect ocean circulation. There is a very strong new, somewhat speculative paper published last week by Jim Hansen's group with 15 co-authors on what happens as the ice melts, and it's like you're hosing the ocean with a hose of cold water being sprayed around Greenland and Antarctica, which will somewhat change the ocean circulation there, causing more or less deep water formation and saltiness that will change the circulation. So for example, one prediction out of this new paper is we will see cooling of surface waters around Antarctica in the coming several decades. So instead of seeing a warming due to global warming, the feedback there will be to cool the ocean waters somewhat. So it's a big prediction. We'll see if it happens. Then the whole issue of the oceanic uptake of energy is a major one, because this so-called hiatus that happened in global warming in the last 15 years until the last 2 years was, assuming the measurements are all accurate, probably due to increased uptake of heat by the world's oceans. That can happen again, or it could shut off. You get an additional stability as you warm the ocean surface waters. It's harder to move things vertically if hot water is on top. But there are many other forces at play in ocean circulation. My last slide is simply to say a couple more things. Whether we like it or not, this mathematical modeling of climate is essential. So the people doing this work are some of the hottest young scientists around the world, solving this interlocking system of partial differential equations that try to go from first principles, explaining the energy budget of the Earth's surface, the energy being moved between phase changes in solid, liquid, and water, vapor, water, how you transport all that stuff through a rotating global atmosphere. And then, so some of the key questions are how to continue to improve the geographical resolution of these models so that, for example, Iowa and Minnesota are represented individually in pieces rather than being lumped together in one big piece, or regions that have mountains versus plains can be separated, and then the cloud formations and the rainfall events can be broken down much more mechanistically. A couple of major questions are, in these mathematical models, which turn out to be numerically solved on computers, can we trigger and exit ice ages over long periods of time? Can someone actually explain to scientific satisfaction what causes ice ages, what triggers it, what kinds of feedback mechanisms are in play, and how in the world we get out of ice ages? We know that we do. There are geological and ice records of this, but it's been very hard for people to model the mathematics of this in a dependable way. That's a major challenge. One of the really serious ones is the acidification of the world's oceans. It'll take a long, long time before we actually reach a pH of below 7, but the pH has dropped in a measurable way, and the sensitivity of marine biology to these patterns of acidification around the world, where basically carbon dioxide is taken into the water and you tend towards acidity that way. What are the impacts going to be on individual species and on ecosystems, such as shell-making creatures that depend a lot on the carbonate in ocean water? And then the land surface is involved in all of this. So climate science, as it gets more important, is involving understanding of all of these things. Are the rates of future wildfires going to increase as much as is now projected due to increased dryness, increased temperatures, longer periods with low soil moisture, and so forth? Measuring how carbon dioxide is released from soil organic matter as climate changes, so that what up till now has been a measurable greening, a fertilization of the Earth's biota due to more carbon dioxide being in air, how sensitive is that going to be? And will these other measured increases in the rate at which carbon dioxide is released by the world's biota back into the air, is that speeding up faster than the extra uptake due to photosynthesis? And then, of course, the potential for storing more carbon. So all of these things have to be investigated, and many more. It's an exciting field of science. The implications are great and probably happening faster than any of us expected. So the stakes are very high, and fortunately some progress is being made. But I think the story is pretty compelling about the measured increases being due to human activity in all realms. It's very hard to find any set of measurements that fly in the face of that original premise. So with that, I think I'll stop and thank you. And I think we have some time for some Q&A. Ellen, yes? Thank you.
Thank you very much for this very fine lecture. My name is Peter Joseph. I'm with Citizens Climate Lobby. I want to ask you how you deal with the people who think that it's a vast conspiracy and don't believe the science and think there's nothing wrong.
Well, let me try just to answer your question. How I deal with them is to point out somewhat how science works. Scientists don't become rich and famous by agreeing with what other people have said. Scientists make their claim, and a lot of their ambition is based on showing what everybody else is saying is wrong. Now, of course, that statement gets some disagreement, but I think it's mostly true. I wake up many mornings saying, what the hell could be wrong with this picture? I would love to undercut it, but I can't. And people a lot smarter than I, who spend more time on it than I do, have also failed. The basic theory was proposed well over 100 years ago by Arrhenius in Sweden, and even before that in Great Britain, and Callender in the US. So people have had a long time to shoot at it. Just at the National Academy of Sciences, we've produced, I don't know, 30, 40, 50 reports on this general subject in the last 40 years. And the numbers are remarkably consistent on what we expect, let's say, the global average temperature to be. So I think the solidity of the science is pretty good. And I tell people that you talk to me about a conspiracy, it's impossible. It's absolutely, I think, impossible for any one of us to have convinced everybody else in this general field of a phony proposition. There could be errors, but it's not a conspiracy. That's what I tell people. I have met with resistance for that statement, people saying that I'm wrong, but that's what I tell people.
Oh, hi, Larry Everest, Revolution newspaper, revcom.us. There was one point in your type. First, I appreciated your deconstructing of every possible, at least as I understood it, objection to this inexorable rise of climate change. But at one point in your talk, you made the point that we had to basically get used to the fact that fossil fuels were going to be with us for a very long time, and producing the vast bulk of the energy that this planet uses. And I agree with you on further developing the science. You were making that point at the end, but I just find that prospect intolerable and frightening. In the New York Times today, they were talking about sea level rising 3 to 4 feet, and then ultimately the seas going even 100 miles in. So my view is that this is a political and economic problem, and everything that you have said calls upon us to do what I would consider have a radically new economic and political system, that capitalism isn't capable of resolving this issue, that we need a revolution and this new synthesis. I'll stop.
I can't disagree with you, but whatever the solution
is, if I could just
it has
invite
to release
people,
a lot of energy, physically. That's all I'm saying.
And I just wanted to invite people to come to the Tilden Room Friday at 6 to talk about, I know we can't tonight. Thank you.
Hi. Something I didn't hear you talk much about, and I'd love to hear you talk about, is feedback effects. Yeah. So the possibility of positive feedback effects and the possibility of negative feedback effects, and which are apt to dominate and over what temperature range.
Yeah.
And in the end, will we be extinct?
Do you have a particular feedback effect that you're interested in?
Well, actually, well, moisture is one I've heard a lot about. Yeah. So there's a physicist at Princeton, for example, who points out that that moisture is one of the biggest warming gases, and maybe heat creates more moisture off of the ocean.
Okay. Well, Will Happer should know better. The fundamental that I think makes you have to take, the numbers I just showed you, this radiative forcing, those things happen in an active atmosphere and ocean. And when you warm a body of water, you release more water into the gas phase. That's what results. The current thinking is it's a positive feedback. That is, as there's a warming, the warming will accelerate, due to lofting more water vapor into the atmosphere, which then becomes another greenhouse effect. What Happer is claiming, and he's right in one respect, if you simply evaluate carbon dioxide itself, you get a fraction of these numbers for a change in carbon dioxide. And you get about double that fraction of warming if you include the increased water vapor that you assume is going to accompany the warming. But the reason that assumption is good is something that in physics or engineering is called the vapor pressure of a liquid at a various temperature. In this case, the Clausius-Clapeyron equation, which describes the equilibrium of a gas above a warming liquid. And it's a strong function of temperature. It's not a smooth rise. It's a parabolically shaped curve that goes like that. So there's a lot of potential for feedback. So as you warm the planet, the bodies of water warm, and the equilibrium water vapor above in the air increases more strongly than the rate of temperature increase. It's called the Clausius-Clapeyron effect. And there has been one notable scientist who said that he doesn't believe that this feedback effect will be so positive, and he's tried to find ways that the atmosphere will become drier as you warm up bodies of water beneath it, and he hasn't been successful, and he won't be successful. This Clausius-Clapeyron effect, any of you know the details yourself, you know that it's pretty fundamental. So that's one feedback. Now, there's an interesting aspect of that. If you put more water vapor in the air, which is going to happen as it gets warmer, you'll probably create more clouds. And this is a really interesting feedback. Will the clouds cover the sky more in terms of cloud cover? So there will be less fraction of the sky where you see it's blue because it's covered by clouds. Or will the clouds instead grow vertically? Let's say with the same cover, but they grow deeper vertically. In the latter case, it's a positive feedback on climate warming. And the previous case, where you get more cloud cover, you actually then can reflect more sunlight back out to space, and you can get a cooling. The current understanding of cloud physics is that the positive feedback is going to dominate. So in all of the mathematical calculations that have attempted to understand that feedback, it comes out positive. But it's not necessarily definitely true. It probably is. Looking at data sets from satellites, you get supporting evidence for the positive feedback. And there are many other interesting feedbacks in this system. For example, there's a lot of organic material stored in peatlands and clathrate deposits in ocean margins, where a little bit of warming can make those release carbon dioxide and methane explosively. So you can get sudden injections of greenhouse gases with just a little bit of warming. There's other ones about snow ice. As the sea ice disappears in the Arctic, sunlight now sees dark water instead of white ice. So the sunlight itself is absorbed more by the water. That's a positive feedback. And there's just feedbacks all over this system. And are we modeling them all perfectly? I doubt it. But the other tendency that's showing up as a positive or a strong feedback is the intensity of rainfall events. I think it's now been shown on 5 continents, if not 6, that the frequency of heavy rainfall effects has increased in observations. This is due to the fact that there's more moisture in the air, so that when it rains, it's more likely that it's a heavy rain. But it can still be dry in between. So all kinds of feedbacks here, and they're tremendously important, and we don't have all of them nailed down yet. But the water vapor one, I think, is pretty solid because of the Clausius-Clapeyron effect. Yes, sir.
Dr. Cicerone, thank you very much for a fine presentation. I'm also interested in your views about the feedback effects from the stored carbon in the permafrost in the Arctic. You showed that the average temperature of the Arctic in certain regions increased by more than 10 degrees centigrade. I'm wondering, are you very worried that perhaps an uncontrollable feedback effect could be induced in the Arctic,
Yeah.
where
Yeah.
1.5 trillion tons of carbon are stored.
Yes, but again, I don't think we have very good predictive capabilities. The current thinking is it's going to take hundreds of years to really release a lot of carbon that's now in old vegetation in permafrost and buried deep as methane gas or even coming out as carbon dioxide. If the permafrost melts and dries up, we will get carbon dioxide release. If the permafrost melts and leaves a pool of water, we'll get methane release. But the question is, how soon? This warming of the Arctic is more than anybody expected and faster, but there are still lag times built into the system that I think will stabilize it. The difficulty in conducting heat down even 5 meters, it takes a long time for the thermal conductivity to work to conduct the heat down. So most of what's happening now is on the surface, and I'm not aware of any indications that methane releases are increasing from the Arctic. There is more carbon dioxide that's being released, but it's a pretty small amount compared to all the, so far, compared to all the other releases of carbon dioxide. But in principle, yes.
Hi, Jim Hammett. I wanted to ask you, on the maps you showed us of the temperature record in recent hot years, there tended to be one cold spot in the North Atlantic around Iceland. And is that kind of well understood?
I don't think so. I don't think so. There are some very good meteorologists and physical oceanographers who are arguing about it. For example, if you look at the geographical patterns of the winters in the Northern Hemisphere in the last few years, we've had some cold eastern United States winters. And there's a lot of argument going on now how that's connected with the loss of Arctic sea ice with mechanistic understanding. There are some oscillations that observed in the North Atlantic water flows that last 30 or 40 years each, one of them 70 years each, so we don't have enough data record to know exactly where it's coming from or the mechanisms of it. I think it's a puzzle. There's very little. One of the gross indications that this is an unprecedented kind of climate change, not only that the forcing conforms to what humans are doing and the numbers are right, but the fact that the warming is pretty ubiquitous. If you average over a period of a few years, you cannot find a place on the Earth that's cooling, that's more than a microsite. And in previous climate changes that have been observed, like the European warm period in the 15th or 16th century and so forth, there have been regional patches of warming or cooling, but nothing this global before. But you're right, there is that fairly persistent pool of cool water above the north. And some of these temperature records that I told you that people work on somewhat in competition with each other, they have different methods of sampling the Arctic. And some of them, the British record undersamples the Arctic. So they tend not even to see that cold period. And in turn, they get lower measurements of global average temperature rise because they're ignoring the hot spots in the Arctic. Not completely, but relatively. So there are a lot of details like that that could be important that are not clear yet.
Thank you very much.
Thanks, Ella.